Oh shit. All right, let's do it. Let's do the thing. Man, what a week. Literally what a week. I need like my stocks to go up. That would be nice. I would really like that. Uh I don't know if anyone's running again this week. I kind of put this in the middle of Friday and it kind of works best for me, but it doesn't always work best for everybody else. So it's possible that this is just a bad time for book club. Plus, this book's kind of hard. Like, not hard. Maybe it's not hard. This book's interesting in that, like, it is a technical book, and while the author made it really easy to like work through and whatnot, the concepts are still technically difficult. So there's not as much like to discuss per se because it's very clear what's happening under the hood. So yeah, I don't know. I don't know what book I'm gonna read next. I might shift to the compiler book, or I might shift to a different book. We'll see. I'm kind of reading a few right now, but I don't know if there's any ones that I would want to do another book club on. Running book clubs are hard, so we'll see. But I will wait like a minute, another like minute or two before actually getting started. And of course, as I start streaming, then I get emails and stuff, of course, every single time. My voice is also a little shot because, went out and did things. Let me get the source code up and running. Yeah, perfect. Okay, let's go for it. I'll record it either way. I share this with like the channel that I have. And people watch afterwards. And plus I have a hard stop at the hour. So cool. This is the book club for the going to the top. I guess there's no way to skip to the beginning. Writing an Interpreter. Great book. This walks you through how to write an interpreter using the Go programming language. So the interpreter will actually lex your source code, parse it into an abstract syntax tree, evaluate it, and actually do things with it. So we've already covered chapters 1 and 2, which are lexing and parsing. And now we are on chapter 3, which is evaluation. So evaluation is interesting. There's a few parts of this chapter that I want to talk about and call out just because they made me like think a little bit. So the whole purpose of evaluation, right? Like when you do it, when you have an interpreted language, I'm gonna put this aside for a sec. But when you have, I guess I can pop this in and out like that. Cool. When you have an interpreted language, and let me actually like get out of here. Let me just do like Python 3. If you have an interpreter or an interpreted language, all your source code, right? So if I do print like, hello, all your source code has to go through an interpreter, be lexed, be parsed, be evaluated, and do the thing, right? So you'll see here that this print hello actually was evaluated, and I got the result hello back. And if I did like, Python doesn't have let, sorry. If I did x equals 2 plus 2, and then I did x, you'll see that I have 4, right? So this is actually getting evaluated. It's taking the expression 2 plus 2, it's evaluating to x, it's storing the result in x, and then every time I use x now, I get 4, right? So we as engineers use interpreters all the time. We even use it in like, I don't know, let's do like a bash script, right? So if we do like hello.sh, and if we write bin bash echo hello, right? If we do this, and I can do that chmod plus x, and then I'll just do temp hello.sh. If I run this is actually being interpreted, right? So even though like this is source code for the bash shell, and you're saying, hey, run this source code through this bin bash interpreter, and then here's like statements from it, right? Or expressions. And when you hit echo hello, it actually performs the operation and like evaluates to hello. So interpreters are like all around us, which I thought is pretty interesting. Depending on where you are in software, you've probably experienced an interpreter in your life, right? And this monkey interpreter is no different that the author's having us write. So now I've dropped into the monkey interpreter. I can do let x equals 5 again. And if I do x, I'll get 5. No matter how many times I hit x, I will get 5. If I did did we do puts? I don't even know if we did a puts in this. I don't think we did anything here. Okay, yeah, we didn't do puts yet, but we didn't extend the parser. But if I created let me actually control C this and go back in. If I create it like, I don't know, let add X, and then it should like let's just do like 2 plus, God, I can't type. If we did this, if we do let add, oh, sorry, I did my token wrong. I think it has to be like let add equal fnx. Let add equal fn of x, and then 2 plus x. I think it's this, yeah. So now I have the function add. So if I like just ran it, it'll say here, you have a function. But if I did add and then like 2 plus 2 is 4. If I did add 10 plus 2 is 12, right? So we are actually evaluating this and storing it. So this is the whole purpose of this chapter. And I thought this was cool. And the thing I wanted to really talk about here, oh, I don't have any money to get it, but I'm using Java for my interpreter. Nice. Oh, hey, thank you, man. Appreciate that. Yeah, I bought the physical copy. Yeah, I have the physical copy, but then I also have the virtual copy just because it's easier to like stream it. So I thought this whole thing was cool, right? We have the ability to lex our tokens, parse them into an abstract syntax tree, but now we actually have to do things with them. We have to give them meaning, and that's what the author kind of goes over here. Give them the meaning, give these tokens, give this AST meaning, right? Like when I do let num equal 5, I am literally saying that we have to remember num has the value 5, because when we use it in the future, we need to know like what to do with it. So this was like the first part of the book. And the author goes in and says, like, there's different strategies that you can use to do evaluation, right? You can actually, the line between an interpreter and a compiler blurs a lot, because technically speaking, an interpreter does have to build some sort of like bytecode or machine code or something that needs to be executed. And technically a compiler really does that too, right? A compiler builds machine code. So the author really just says the line blurs, but don't worry about the nomenclature so much. We are building an interpreter, and this interpreter will actually evaluate our AST and start actually giving us results back. And he says the interpreter that we are going to build, like the evaluator, is going to be one that's called a tree walking interpreter. And there's many different types of interpreters that I didn't go research, right? I didn't go research interpreters. I've been a little busy this week, so I didn't go out and like do extra research. But there are different interpreters out there, and the one that we're going to use is a tree walking interpreter. So we're literally going to like start at the root of our AST and start walking it all the way and evaluating every node and every expression on the fly, right? No pre-processing, no compiler optimization steps, none of that. We're literally just going to walk the tree, similar if you've ever done programming on trees, like a binary search tree or something. We're just going to walk those nodes and use recursion to go through them, which is kind of cool. So that's the type of interpreter we are going to use in this book. And the next chapter is where things get pretty interesting, because we need some way to represent these objects that we're running into as we're traversing the abstract syntax tree. And you can see that the author says, like, what would this actually mean? If we did like let a equals 5 and we did a plus a, we need to actually remember what the value of a was. So we can't just parse a node, go to the next one, keep going down, evaluate a node and keep going down. We have to remember what we've evaluated, because we might need to see it again in the future. So the author, like this whole source code, like this all, I'm going to skip the like actual text, but the author says to do that, we need to create a new type in our language that will hold the actual object that we are evaluating. And the two like pieces of behavior we're going to give that object are the ability to tell it what type of object it is and to inspect things about that object. And we start with like integers and we go down the gamut. And I'm going to open up the source code in my editor in a second. But we start with integers and we build a new type that implements the interface that we just built before, this object interface. Actually, it might make sense to open this up in my, this actually might make sense to open up in my source code. It's probably easier to follow. Let's do object. The object, which is actually funny, object. Okay, so you put environment here. Yeah, okay. Object, nope, sorry. Object, this one. So we need to represent every single node that we're traversing as what we call an object. And the reason why we need to do that is because we're gonna have many different types of nodes that we run into, and we're going to need to like hold on to their evaluation values, right? So we need to know their type and what's inside of that. And basically we're going to be creating new specific types that implement this new object interface to cover all of the various sort of types that we can evaluate in our AST. We can run into integers. We can run into Booleans. We can run into nulls. We can run into return values. We can run into errors. We can run into functions, right? And I'm just highlighting these a little quickly just to show you. So these are all the possible objects that we can encounter as we're doing the tree walking of our AST. So I thought this was pretty cool, and it's pretty straightforward if you kind of read the code. We just define a bunch of like constants for the types so that we can do assertions. So we have a null type, the error type, the integer type, Boolean, the return value, the function. And then we create their actual struct types underneath, and you'll see that the type just returns the constant, right? So that we can know what type of object this is. And then the inspect just returns the literal like value for that object. So here we are just taking the underlying value that we got from our AST, and we are just giving its value back. So it's pretty cool, right? I thought this was pretty interesting. And we're kind of piggybacking on Go's underlying types here to help us out, right? When we encounter an integer in our AST, we're storing it as an int64 in Go. If we encounter a Boolean in our AST, we're storing it as a Boolean in Go, and so on and so forth. So I thought this was pretty interesting. Under the hood, like this seemed much more this seemed simpler than I thought it was going to be. So I was kind of shocked. And we'll get to the function side later where it gets a little messy. Let me go back to the book. So the author gets us to the point where we evaluated like the literals, right? A literal integer, a literal Boolean, and a literal null. Like we've evaluated them. Then the author says that's cool, but we also need to evaluate expressions between these things, right? You can have like the literal integer 2, but you also want to evaluate the expression like 2 plus 2, and you want to get 4, right? You want to get 4 back from that. So the author, like, again, builds test cases, and he says, in order to actually represent these, like as we're traversing the actual tree, we need to now make decisions on what sort of type of node we have and parse them and evaluate them similarly. So here's where we're going to go into the evaluator package, and I'll show you what the code looks like. Evaluator, yeah. So this package is going to look pretty big. It's 325 lines, but we're going to break it up a little bit just to show you like step by step. There's this like global, I think I can actually show you, what is it? I think, yeah, there's a bunch of methods and functions in this file, right? We have the actual eval, which everything kind of flows through. And then we have all of these helper methods that help us evaluate our AST depending on certain operations happening, right? Are we evaluating an infix expression? Are we evaluating like an integer? Are we evaluating this or that? So we have all these helper functions here, and I'm just listing them here just so you can see them. It's a little easier to see like the functions rather than scrolling through the source code. But everything flows through this eval function here. So this eval function takes a node in the abstract syntax tree, so whatever node that we're currently on, and ignore the environment for now. That's going to come up in a second. But every time we receive, like as we walk the abstract syntax tree, we have a node. We need to evaluate that node. And this evaluate function takes care of that evaluation. It says, hey, if the node that you're on is a program, evaluate it as a program. If it's a block statement, evaluate it as a block statement, and so on and so forth, right? And we have many different cases here that we can walk down depending on what node we're on. And you'll notice this is kind of the translation period where a AST type turns into an object type here. Because remember, this AST type is from the AST package. So if I get a program, if I get a block, if I get an expression, evaluate them accordingly. If we look at the integer stuff, the integer literals and the Boolean literals, they're pretty easy. So let's start there. If I'm walking my AST and I come upon an integer literal type, well, there's really nothing else to do, right? We know it's an integer literal, so we can literally read the value from the node itself, right? And this is coming from the AST package because an integer literal AST type has the token and an actual underlying value. So since this was already done, we can just say, great, we found an integer literal, build a new integer object and store the value that we had in there. And we do the same thing with the Boolean, right? So it's not bad. Like the Boolean is just if true, return true, otherwise false. So this is like the inflection point and where a AST type converts to an object type. I thought that was really cool. And then expressions. Expressions were interesting. Let me go back to the book. So the author says we have to actually store these objects somewhere so we can actually evaluate them, right? So we know that now at this point, we have, I didn't show this part actually. This is what I want to show, which was, sorry, I know where it is. It is, let me go up. It is this. Not this. I think it was, yeah, it was here. Yeah. So the evaluator does eval. Yeah. Okay. I want to show that we actually call this in the Repl Go. So as we like scan our source code, so not only are we lexing it, not only are we parsing it, but now we're also going to evaluate it. And how are we going to evaluate it? Well, we're going to call the eval functions for that. And the eval function will now walk this AST. And you might be asking yourself like, hey, Matt, like how the heck does this eval actually walk the tree? Do you have a dictionary containing all the keywords in the monkey language? I don't. I thought he like put that. He might actually put that in the next like chapter. I thought the author did actually put that. Maybe it was in, oh, sorry, I didn't mean to open that. Maybe it was in the token package. I think these are all of the keywords and everything else is like an operator or whatever. Yeah. So in the token package, which we covered in chapter 1, when we lexed the source code into tokens, we defined our like programming language keywords in here. So it's in token.go in the source code for the book. I can actually send the link to the source code. I think it's in the beginning of the book. I wish I had 2 screens again. This is where having 1 screen sucks. I think they put it, how to use this book. Yeah, copy link. Awesome. That's the source code. So you can follow like along at least the source code. So in that source code, you'll find this, like directories numbered 1 to 4. Each directory is like corresponds to a chapter in the book. So like after chapter 1, you'll have like certain source code. After chapter 2, 3, and 4, you'll have certain source code. But what you're asking about is in the token.token.go. That's where all of like our identifiers, our operators, our keywords, everything's defined here. So yeah, just letting you know. Cool. Let me go back to evaluator for a second. So as we eval, you might wonder like, how are we actually walking the tree then? Well, we're walking the tree because we're recursively calling eval depending on what type of actual node this is. So if we encounter an expression statement, well, then we have to evaluate that expression statement, passing in the actual expression. So we're recursively calling ourselves again and again and again until we've walked the entire AST, or we encountered an error and we returned early. So anytime you see like these calls to eval here, This is us walking different parts of the tree. And that's how we're actually going through this stuff, which I thought was pretty cool. And each call to eval like will return up to its call stack, and we recursively walk. So if that wasn't clear at first, I hope that makes it a bit clearer. Because to me, I know that felt a little weird at first, because you're like, wait, how are we actually walking the tree? I don't see like, for range node or something. Like, how are we doing it? This is how. And I guess one of the methods that are doing a lot of heavy lifting is this eval program, this function. We give it an entire AST program, so like the entire program file, and we tell it to walk through the statements in that program and call eval for each statement. So this is where majority of like the tree walking will actually occur, because we'll walk through each statement by statement, calling eval for each node in the statement. Cool. After that, so that's pretty obvious of like what were happening. After I got through section 3.4, towards the end, I like understood what the author was getting at, right? We need some way of taking the AST and storing it as objects for us to use and inspect so that we can give the results back to the user. But the harder objects to evaluate were expressions. And the author spends a good part of the book here, like talking about expressions for a second, because he says that like it's easy to parse and evaluate literals. We know how that works. But when you have expressions like 1 + 1 or 2 + 2 or whatever, it's harder to evaluate them. So the author did that by bringing up these like expression statements. So if we have an expression statement, we have to evaluate that and kind of walk that recursively. So that's what the author kind of made us go through here. And you can see that in the book. You can see that he did, that's the tests. He added support for like integer literals, which we did, but then he started adding the case for evaluating an expression statement. So you can see that an expression statement will break down the expression and then actually break down like the literals that are in their expressions. So I thought that was pretty interesting. It was pretty simple to make that test case pass, because all we really had to do was walk, like just recursively call ourselves. And I thought that was interesting. And at this point in the program, we were able to do basic expressions like 1 + 1 and get the actual value from them. So I thought that was cool. What else? What else was like sticking out on me? The error handling stuck out to me, and I'm going to get to that. Yep, he showed us the evaluator. That's great. And he showed us integer literals, Boolean literals, null. Okay, yeah. And then we had to do expressions. Yeah. Perfect. Okay. So once we had our REPL, I'm going to actually start our REPL real quick. Once we had like this working, like 10 giving us 10 and like, true giving us true, we needed to start doing like 1 + 1, right? Like actually computing the result of this. This is where we go back into doing the prefix and infix expressions. So I'll actually open up the code. Vim evaluator. Yeah. So this is what prefix. Yeah. So we added these two cases to the actual evaluator, and we said, hey, if you end up on a prefix expression, I need you to evaluate the right side of that, because I need to know what I am actually prefixing, right? What my prefix expression is actually affecting. And you'll see that we do that. We evaluate the right side. So let's say in this case, we got -1 as our prefix expression. We would first be on this node, on the negative token, right? And we'd see like this is a negative prefix expression. We would then evaluate the right side, which is 1. That will call eval with like, so essentially this call right here is calling eval of 1 and like passing the environment in, but we could ignore that. We know that the 1 will call eval, hit this integer literal case, and then just get 1 returned as an object. Once that returns, we will have like right, like this right object here, this right return type would be a integer object holding the value 1. and we check if it's an error, which it's not, and then we evaluate the prefix expression with the operator that we're on plus what we got from the right side. And just walking that just a little bit further, and let me actually there you go. Walking that just a little bit further, let's go in there. You see that the only prefix expressions that we support are like the bang operator or the minus operator. And in that case, if we were parsing that -1, right, if we were evaluating the -1, we would fall into this case. We would then go and say, hey, if I received a negative prefix operator and I now do not have an integer on my right-hand side, that is an evaluation error, because you couldn't do something like negative, hello, like a string. You couldn't do this. That's going to be a parser error for our monkey language. Otherwise, if we do have an integer, we're good. Get its value and return its value back up the stack, which pops us all the way back up to here and lets us keep going in our evaluation. So a lot of recursive, honestly, like a lot of recursive nature like happening here, which can be a little like mind bending, because you're sitting there like, wait, how the hell am I like going from here to there, from here to there? It's just recursion all the way through. And that's kind of annoying, but that's basically what's happening here. And now that we talk about the prefix expression, like -1 or whatever, we can talk about infix. So infix would be like the case where you get something like this, where you get like 1 plus 1. And it's no different. We have to evaluate the left-hand side, right? So we have to evaluate this 1. Then we have to evaluate the right-hand side, which is this 1. And then we call evaluate infix expression. And all this does is says, hey, if my left and right are both integer types, then evaluate them as, an integer plus an integer, or integer operator integer. If the operator is like an equality operator, then you have to try to convert the left and right to Boolean expression. If the operator is not equal, do the same thing. And if the types do not equal, so if you did like 1 plus hello, this ain't JavaScript, right? This ain't freaking JavaScript crap. Then that's a type mismatch, return an error. Otherwise, you have passed us an unknown operator, and that's an error. So I thought this was cool, and I'm gonna like annotate these real quick. So this would be the case that both of these are integers, so like 1 plus 1. This would be the case of an equality operation, so like 1 equals 1, right? And this would be the case of like 1 does not equal 1. This would be the case of like 1 plus, foo, like a string, because these are type mismatches. And this would be the case of like, 1, I don't know, ampersand 1. We don't support this ampersand operator, so it's unknown. So this would be like the cases that these will fall into. And once we did all that, we basically have most of the program running and parsing. And now we have expressions working and everyone's happy. So I thought that part of the book was interesting. A little hard to wrap my head around when I read it the other day, because I was like, wait, why are we making so many extra functions to do this? Why aren't we doing this in one function? And the author says just for testability reasons, honestly. So I thought that was cool. Then we went into conditionals, which I thought was interesting. So I'm going to actually cover, I think he did conditional. Where did he put it? I think it was, if expression. So the only conditional we have is an if. So we evaluate that. And I thought that this was a pretty clever, I guess is the word. I thought this was pretty clever of the author to do this. So when we evaluate an if condition, like when we get to an if condition in the source code, we evaluate it and we say, hey, tell us, like evaluate the condition itself and give me back like the actual condition that we're doing. And then the author says, we can't possibly evaluate both halves of a condition, or like, all branches of a condition, right? If, else, if, right? Like we can't evaluate every branch, because not every branch is valid depending on what we're evaluating to. So the author did that here. He's basically saying, if the condition we got back from that AST node, if that is a truthy condition, only evaluate the truth part of our condition, right? So what this is saying, if we had like, if, 1 greater than 0, foo, and then we did like, give me that, there you go. Else bar. If we had like a monkey expression like this, if 1 greater than 0, give me foo, else give me bar, then if this condition was truthy, only evaluate this foo section. We can literally ignore all of this. We should not have to evaluate it. In fact, if we did evaluate it, we can run into errors. So we should never evaluate something that we should not, like the conditional doesn't give us to. So that's what's happening in this block of code down here. It's basically saying like, if we should enter the truthy part of the evaluation, go that way. Otherwise, if the alternative has been set for this AST, just evaluate the alternative, which in this case will be bar. Otherwise, if we just didn't enter this at all, return null, because there's nothing here to evaluate. That would be like if we just had a single if condition like this that said if 1 is, equals 0, this is obviously false. So we should never evaluate anything in here and just return null. So I thought that was cool. And it was a surprisingly little amount of code for what I thought was going to be a complex thing. So I was happy to see that with the author. And then return statements were interesting because this was the first time that we were doing like short circuit operations where we were returning early. And you can see that in the code. Back to the code. Return. Oh, this is gonna suck. I think it was this one. Yeah, if it's a return statement. The only thing we have to do here is once we hit the statement that should be a return statement, evaluated, and actually return its value upwards to be evaluated, to be like unwrapped. So let me show you what that means. Go back to eval, and I think it was in here. No, it wasn't here. Where did he put that? Let me just double check the code here. And eval statements. Perfect. Thank you. Eval statements. I forget what that was. I think that was actually in, where were you? You were in evaluator. Yeah, this is what I wanted. Oh, this might actually have been overwritten by the time. I just want you, honestly. One sec, sorry. I just want you. Yeah, that's what I want. Okay. So the thing with returns are, if we encounter a part of the AST where we're actually returning a value back to the caller, then we need to not short circuit in the evaluator, but pass that back up to the entire program evaluation so that it can determine whether or not the result we got back from the evaluation was a return value or an error. So like this was an interesting thing. And the author even notes this in the book. He says like, we wrap the result of this so we can keep track of it, but then we pass that back up to like our eval statements function, which actually gets refactored later in the chapter, to then do the actual checking of whether or not the returned value was a return value or an error, so we can keep track and like print to the user. So this was interesting. I thought this actual like part of the code was a little hard to follow at first because it was not clear to me at first that why we weren't returning, like why we weren't doing this like assertion earlier. I didn't know why we were passing this up at first until the author told us about like, we can technically have nested returns, right? Like a function can have a function inside of it or whatever. And that started making sense. So that was pretty interesting. Then there was error handling, which I thought this chapter was going to be huge. I thought this chapter was going to be like 10 plus pages, but it ended up being like 4 pages or whatever. Yeah, it was like 4 pages. I thought this was going to be huge, but the author basically told us anywhere that we were returning like null, we can just go return errors instead. And I thought that was pretty interesting because if I show you like all the calls to like new error. So we have 8 places where new error is in this file. One is if we have a prefix expression that we don't know. I'll invite Max to speak. Two is if the infix operator has two different types on both sides.
Hello.
Hey. Three is if we got a operator that we didn't know how to use. Four is again like we had a
I'm on
minus.
Discord.
Hey, what's
I
up?
think I'm muted.
No, you're not muted. I hear
I'm
you.
not muted.
You want
Not
me to mute
you.
you? Hey, I'm streaming the book club. What's up, man? But yeah, this other one was if we had like
I don't
up.
hear Matthew speaking.
Oh, you don't hear me at all? Oh, it's probably because it just tune into the stream. I'll give
My
you the stream
Discord's
link.
super broken. Hold on.
All right, I'm gonna mute you again for now. I love you. This type is when we had like a negative sign in front of a non-integer. Then we had like, I think Max is back. Let me get him back up here. Cool. Unknown operator again. I could unmute you. Sorry.
I see you talking on your live stream, but I don't see you
It's fine.
talk. I don't hear you.
It's fine. I know you don't hear me, but I'll give you the link to the stream.
This is
Actually,
lame.
sorry, Max. I love you, man.
Why can't I hear you?
Sorry, buddy. Max. All right. Anyway, so
Hold
yeah.
on,
All right, I'm gonna let you deal with that, Max. I love you though. So yeah, basically what the author was saying here, which I thought was cool, and okay, it's only 34. We're good. Is everywhere we saw
Okay,
that?
can you hear
null,
me?
I
I
can hear
see.
you.
I just saw your message.
I can hear you. You can't hear me. Let me just double check that. You probably can't hear me because OBS probably stole my mic from Discord. Hard to say. Tune into the.
Oh yeah. Wait, can I? If I'm watching the live stream too. I'm surprised I can't hear you
Yeah,
either.
you should be able to hear
Through
me on the
here.
live stream because I can hear myself in the live stream. So I think it should be good.
Hmm.
Oh, I can hear myself
Tune in. Oh,
on
okay.
stream. So I'm not sure what's up with your stuff. Okay. All right, I'm gonna mute you for now. Anyway, so where's that? I thought this error handling stuff was gonna be a lot larger than it was, but it ended up not being. And I thought that was interesting for the way that we designed or the way that the author designed this whole parser or this whole evaluator. And it's basically just putting an error, returning up the stack, and then we get to do the like case check whether or not we got an error back while we were evaluating our whole program. Did any statement return us an error? If it did, we're done. Return the result. So I thought that was pretty interesting. What else? There's one thing in this book that in this chapter that really got me. Oh, yeah, it was the bindings. I thought was pretty cool. I'll bring Harm up. The bindings and the environment. I thought this was actually really interesting because I always knew like what I'll unmute Max's case. I always knew like what like the environment meant, and I knew why we cared about this, right? When you have like nested functions, you know that like the inner function should be able to shadow variables from the outer function and all of that good stuff. Like, you know that that's a true thing, and that's great. But I didn't understand how this worked under the hood until I read this section of the book. So basically, and I think I can just show you the source code better. Environment. Oh, sorry. I think that I'm gonna quit that. Did I actually? No, I'm good. Yeah, object environment. So this was pretty interesting. Scopes. Yeah, scopes. This was a pain in the ass. So the author says every statement needs to have its own environment. And all the author built was a little wrapper around a map in Go. So like you can store a map of string to the object. So when you do like, let x equals 5, you will get an entry in the map of x with the value 5, right? So that's all you'll get. And this allows each statement to keep all of its state, keep its scope for the next one. The earthquake was fun. My house was shaking for like 15 seconds. It's kind of crazy. Where was he? Oh yeah, right here. So env. So let's look at that for a second. In order to make this work, the author had to update each call to eval with and pass the environment through, right? And the environment is a pointer to an actual map. As we like go through env here, you'll see that we're passing it to every place that we call like eval. What's cool though is that when we actually get to statements that need to set the environment, we explicitly call that out. So like a let statement, right? If we have let x equals 5, what are we doing here? We evaluate the value. So we found 5. So at this point, val is 5, right? Val is 5. And what do? We store that in the environment. So we do like, map of x equals 5. And we do that again and again and again and again. And I thought this was pretty cool. It uses Go's like map under the hood to kind of just store state for the scope of your functions, or the scope of your AST. We also did that though with not only lets statements, but functions. So functions were also allowed to set their own environment. And this basically gives us the ability to have closure functions whose environment doesn't overwrite their parent's environment, but it simply extends it. So I thought this was pretty freaking interesting. And I think he gives a good code example on this. Let me just find it real quick in the book. I think he does a closure. Yeah, like right here where he does, I think he does this better here. Yeah, new adder. So he does like this closure here where it says like let new adder equals a function of x that returns a function of n. And I thought this was interesting because here, this, whatever you pass in to like new adder, so like new adder of 2, this is stored in the environment for this function. But then now every time you call that function, it also gets a new environment that's allowing it to read from the parent environment. And he shows this with the I. Hold on, he shows this a little later in the chapter. Yeah, he shows it right here, which I'm going to make this big for a second, where he says, the reason why we needed these two environments that have different scopes is so that we can do something like this. We can do let I equals 5, and now here I is 5. But then we can define a function that takes a parameter called I and can like print it out. This I should not be the same as this I. And that's what he was saying. In our previous way of storing environments, these would have overwritten one another. But since we do those like nested environments and we like build new child environments, this I is a different scope than this I. So it kind of shadows it. So I thought that was really, really cool. And after like you read the code, especially the environment code, after you read this, you're like, oh, this is actually simple. Like, look what the get does. It just says, hey, if my environment doesn't have something for this key, search my outer environment, and keep doing that again and again and again until you ran out of outer environments to search. So I was like, this is like 2 lines of code. This is a coding question, by the way. This whole environment stuff right here, this is literally a coding question of how to like build a time like map or whatever, or build like a map based structure, or like what do they call it? Build a key value store that supports like child transactions. Essentially, this is a programming question. So I thought this was a fun thing. And that was pretty much it, because we use the same concept there to handle functions. And I kind of showed you that real quick, but I kind of bounce quickly with it. Since we needed to handle like nested functions, we needed to use the environment and build like those child environments. And we do that here. Every time we get a function that we have to parse, we have to range over its parameters and make sure that we set them in the new environment, that in a new enclosed environment. That way we don't overwrite what's been set by the parent. And that was it. So all in all, not a lot of code for what we actually had to do here. And now that I like looked at this code and walked it, it makes sense. It's still a little like interesting of how we like have all these case statements, but I get why we do this. So I don't know. All in all, I thought the chapter was cool. And what was left? Oh yeah, we'll talk about the trash out for a second. Any questions, comments so far? Let me see what y'all are saying in the Discord, man. How's your earthquake? Oh yeah, shouldn't leave your vibrator on max. Yes. Oh, it's probably me. I think. Here, let me. Yeah, I think it's Discord. I think I screwed that up. Tune into stream. Yeah, sorry. I think usually I have to start. I think I have to start Discord first before starting OBS, but I didn't do that this time. Cool. So at the end of this chapter, we were left with a really nice REPL. Yeah, I don't want to write that. I don't want to write that either. Cool. We were left with a really nice REPL that allowed us to do like let x equals a function of x, which can do like, x. We did this before, x plus 2, or yeah, let's call this like a double adder. So now we have a function called x. And if we did x of 2, we'd get 4. But you'll notice this x and this x are different scopes. So even though like this x is holding my function, this x is holding an integer. Yeah, I'm scared of bytecode too and all that. But that's in the next book, like the other book that he has. So I don't think we're going to cover that. The last chapter of this section was about garbage collection and like who's actually doing the garbage collection for us. And this part was just very simple. The author says, imagine this function where you iterate 100 times or 99 times or whatever this is. Yeah, you iterate 100 times and you create a variable that's not used and you recurse like 100 times. You are literally creating 100 instances of foobar for no reason, right? So I thought this was interesting, and I'm gonna make these. I'll invite them to speak just in case, even though they can't hear me. I thought this was interesting because technically this foobar is just BS garbage that you can't like do anything with, right? And since we're writing our interpreter in Go, Go has its own built-in garbage collection, and it handles that for us. And that's basically what the author's saying. That if we were actually writing this in another language like C, we'd have to care about this, and we would have to actually like write garbage collection logic to like free that memory up correctly, and that would suck. So we didn't have to deal with any of that crap, which I thought was cool. And for bytecode, the author has interpreter book. The author has this writing and compiler in Go. That's where he'll start talking more about that stuff. So this one's like more just interpreter, and the next one will be compiler. But yeah, that's pretty much it. That was evaluation. I thought that was a pretty interesting chapter. Yep, no garbage collection at all for us. It's since we're writing on top of Go, we get the advantage of Go's garbage collection. So like in this code example, we would technically create like 100 we would create 100 nested environments that all have their own version of foobar, and Go would actually clean that up for us. What are these people saying? Oh yeah, maybe it's Discord. Oh yeah, it's fine. I'm about to end anyway. So yeah, that's what the author was saying here. Why do I have Steam installed in this computer? It's fine. I need to I haven't turned this computer on in like a week. It's so sad. Yeah. Any questions, comments, concerns so far? I think we're pretty good. Now we understand why this all matters, and we understand. I actually wanted to run that toy example through the interpreter. I wonder if this will actually like run well. No, I guess it wouldn't have. I'd probably have to type it. Yeah, it's fine. I have to. I wanted to write it through the interpreter and see like what it would have given me, but I can't like paste it right now. It's fine. Cool. I think that's about it. If anyone has any questions, feel free to put it in Discord or in the YouTube stream. But next week we'll be reading the last chapter, which is extending extending the interpreter. So this one is interesting because it'll basically just allow us to create more than just integers, right? We'll add support for strings, we'll add support for like arrays and stuff like that, and make this a little bit more advanced, right? Because right now I could not do this. Sorry, clear. Oh my god, I can't type today. Right now we can't do this, like let x equals foo. This is just an error, right? And we also can't do let x equal 1, 2, 3. Like if we were to do this, that's a problem. So next week we add that. So cool. I will see you all next Friday, 2:00 again for our last meeting for this book, and then we'll be done. And then you should understand and have a really good like understanding of how interpreters work at a high level. So cool. With that being said, I will see you all next week. Unless I'll wait like a minute or two just in case there's other questions. But I think we're good. Let me open up the book back. Yeah, I think we're good. Discord's quiet. Any questions? Sorry for the... Sweet. All right. I will see you all next week. Y'all are great. Have fun. Make sure you do all your coding, ship all the bugs to production. That's the only way to live life. So, bye.